Welcome to Chapter 5, which is on coordination compounds. And this really gets us into what many people consider to be the meat of inorganic chemistry. Chemistry that deals with the D block elements, right? The transition metals. A lot of interesting dynamics in bonding and in structure that can exist in these compounds. Um, and certainly they are more complex in many aspects than a lot of main group elements because, well, you have different types of orbitals involved, different types of involved bonding that can play out. And so first, just wanted to start out with some definitions. What is a complex? A complex um, is a central metal atom or ion that's surrounded by ligands. Okay, well, a ligand is just a species that has a potential to form a complex. So it's a very broad definition. Usually we're talking about metals here, usually transition metals, but you can have lanthanide complexes, you can have S or P block metal form complexes. Um, and you can also have multiple metals in a complex. We'll see that later on in the course. So something that we call a coordination compound, for example, this coordination compound or complex of platinum, is a compound in which at least one ion is a complex. So here we have a neutral molecule, right? So this is a complex. Most people just call it a complex or coordination compound. There's not really a cation and anion, but it's still a neutral compound, right? Here are more clear examples of what people would call coordination compounds, where they have a cation and an anion. And in this case, so this is called potassium ferricyanide, a very common chemical, commonly used. And this, hold on a second, there we go. This, can be broken up. If we were to break this up, we would have a 3K plus. We know potassium is 1 plus, and then we have this FeCN6 3 minus group. And so this is a complex, right? Because we have 6 cyanide ligands surrounded by a metal, an iron atom, and it's together forming an anion. So together, this potassium ferricyanide, since it has at least one ion that's a complex, we call this a coordination complex. You can see the use of brackets, right, to delineate kind of where the complex is within the compound. So here's another example where you have cobalt and chloride, right? So this would break up into, if we were to like dissolve it in water, 3 chloride ions, and then we have this sort of complex with ammonia, and this happens to be an octahedral complex, and so it has 6, okay, ammonia ligands coordinating it, and its total charge is 3 plus. Each ammonia is neutral. You know that ammonia is a neutral molecule, so it's a neutral ligand. And so this means the oxidation state on cobalt has to be cobalt 3 to balance the 3 chlorides. Here's a little bit of a different example where you have 3 you have ammonia and you have cobalt chloride. So this is just showing you, you can have this written out a little bit differently. This would be neutral. You can see there's no brackets here. And so what would this be? This would look like something like this, okay? It depends what isomer you're talking about, but if this is just the octahedral complex, looks something like this, right? Where we have 3 ammonias and we have 3 chlorides, but now the chlorides are bound, okay? So this is a complex. It's a neutral coordination complex. There's not a cationic part and an anionic part. And there's no brackets to distinguish the cationic and the anionic part. So again, the oxidation state here will be cobalt 3 plus. Why is that? Well, because the whole thing's neutral, ammonia we know is neutral, and so the chloride we know is -1, so it has to be cobalt 3 plus. This one's interesting. It's a coordination compound where you see two sets of brackets here, right? So that what that's telling us is we have two complexes in this coordination compound. So usually the cation is actually almost always the cation is written first. And so we have a cobalt uh, ammonium complex. So we can write that out, right? So that means these 6 um, ammonia ligands are going to be bound to the cobalt center, okay? And then we have iron bounded to cyanide in a very similar type of way. Octahedral. Okay, and it's actually a little ambiguous what the oxidation state here is, but we could make some reasonable guesses. We would have to have more information, like the name of the compound. But for example, this could be cobalt 3. We've seen a lot of examples of cobalt 3 here. So this was cobalt 3 plus, and then this would be iron 3 plus. And if we did that, that would make this a 3 minus, right? Because we have, well, let's do this one first. This is a 3 plus. We have all neutral ammoniums. So if it's cobalt 3, then this is 3 plus for the complex. And if this iron 3 plus, well, the cyanides are each -1. We have 6 of them. And so 3 minus 6 is 3 minus. So overall, we got a neutral arrangement here. So that's fine. But just to show you how there's some, could be some ambiguity here, I'm going to get another color and show you that this could be a cobalt 2 plus. Well, let's write it up. 4 plus, actually. That's a pretty rare oxidation state for cobalt, so this is unlikely. If you know some basic oxidation state trends, then you'd be able to say that, hey, this one in black is more likely. But just strictly by how I wrote this, there is some ambiguity. So if this was cobalt 4 plus, and this was iron 2 plus, then this would be 4 minus, right? Oops. So it'd be 4 minus, and so that would be charge balance. But again, a weird oxidation state for cobalt, so it's not going to be that way. But anyway, so that goes to show you that there is some ambiguity when it's written this way without any additional information. Okay. So complexes are acid-base interactions. The Lewis acid is, as a reminder, this Lewis definition, very useful definition that doesn't involve protons. Lewis acid accepts an electron pair. That's the definition. Remember this from acid and accept both start with the letter A. And a Lewis base donates electron pair. So in a complex, the metal is the acceptor atom. It's the Lewis acid. And the atom or atoms on the ligand, those are the donor atoms, which are the Lewis bases. And so you can think like, let's say you're going to make a complex with between nickel and water. You can see the lone pair on the oxygen of the water molecule would be the Lewis base, would make water a Lewis base. Oxygen would be the donor atom, okay, because that's where the lone pair is. And then nickel 2 plus, that is the Lewis acid, it's the metal. That's going to be the center of the complex. And the acceptor atom, well, there's only nickel there, so that's the acceptor atom.